Somewhere, something incredible is waiting to be known, Carl Sagan. Pulsars are among the most enigmatic objects in the universe, cosmic lighthouses that defy comprehension with their precision and mystery. These ancient remnants of massive stars, born in the cataclysmic deaths of supernovae, stand as beacons of time and space, carrying secrets of cosmic evolution. A pulsar is a neutron star, a sphere of matter so densely compacted that a single teaspoon of its substance would weigh billions of tons. These stellar remnants spin at incredible speeds, emitting beams of radiation that sweep across the cosmos in perfect rhythm. Some rotate just a few times per second, while others complete thousands of revolutions in the same span of time. What makes pulsars truly remarkable is their consistency. Their rhythmic pulses are so precise that they rival the accuracy of the most advanced atomic clocks humanity has ever created. But beyond their regularity lies a tantalizing mystery. What do these signals tell us about the universe? Each pulse is a message, a relic of a star's collapse into unimaginable density. When a massive star runs out of nuclear fuel, its core implodes, triggering an explosion that can outshine entire galaxies for brief moments. What remains is a dense core, a neutron star, left spinning by the immense forces of its birth. Pulsars emit beams of electromagnetic radiation as they spin, creating the illusion of a cosmic lighthouse blinking in the void. These beams, traveling across vast distances, carry with them imprints of the environments they pass through. The interstellar medium, the plasma, magnetic fields, and particles between stars, alters the signals in ways that help scientists map the structure of our galaxy and beyond. Some pulsars, known as millisecond pulsars, spin with staggering speed, completing up to 1,000 rotations every second. These ultrafast rotators are the result of interactions in binary star systems, where a pulsar steals material from a companion star, accelerating to incredible velocities. These systems reveal the dynamic and often chaotic dance of stars in the cosmos. And then there are pulsars located near black holes, where the laws of physics are tested to their extremes. In these regions, gravity bends spacetime, twisting the very fabric of the universe. Pulsars in such locations serve as natural laboratories for exploring Einstein's theories of relativity, offering glimpses into the interplay between matter, energy, and spacetime. The signals from pulsars are not just markers of their own existence, they encode information about the universe's grandest forces. Gravitational waves, those ripples in spacetime first theorized by Einstein, have been detected by observing the slight variations in pulsar timing as they ripple through the cosmos. Imagine these pulses traveling across the vastness of space, spanning millions of years before finally reaching us. They are whispers from the edge of time itself, remnants of a universe far older than our species, older than our planet, and older than the stars we see in our night sky. What happens within a pulsar is nothing short of extraordinary. Beneath their dense crust lies a core of neutrons, packed so tightly that they may form exotic states of matter, like quark-gluon plasma, the building blocks of reality itself. These extreme conditions, beyond anything we can replicate on Earth, push the boundaries of physics and hint at realms of nature we have yet to understand. In their precision and beauty, pulsars challenge us to think on a cosmic scale. Their signals pulse not only with the rhythm of their rotations but with the echo of time, telling stories of creation, destruction, and the forces that shape our universe. Pulsars also remind us of the fragility and fleeting nature of existence. These beacons, endlessly spinning in the dark, are relics of a process billions of years in the making. And yet, they endure, marking the passage of time in a cosmos that is vast beyond measure. The story of pulsars begins not just with the death of stars but with the birth of understanding. When Jocelyn Bell Burnell first detected the telltale signals of a pulsar in 1967, the discovery was met with wonder and confusion. These perfectly regular pulses, beaming with unerring consistency, were unlike anything scientists had encountered. For a brief moment, they were even nicknamed LGM, Little Green Men, as the signals seemed almost too perfect, too engineered, to be natural. But the reality was even more extraordinary. What Belle Burnell and her colleagues had uncovered was a new class of celestial objects, revealing phenomena that defied imagination. Since that first detection, thousands of pulsars have been identified, scattered across the Milky Way and beyond, each one a unique remnant of a stellar demise. These cosmic clocks are not static entities. Over time, their immense rotational energy is gradually drained as they emit radiation, causing their spins to slow. Some pulsars, born spinning at hundreds of rotations per second, now tick away at a more languid pace. But others, known as recycled pulsars, defy this aging process. They are revived by the gravitational dance of binary systems, where the transfer of mass reignites their rapid spins, giving them a second lease on life. Each pulsar is a story of survival in the face of unimaginable forces. Their magnetic fields, trillions of times stronger than Earth's, channel streams of charged particles into jets of radiation. These jets sweep across the cosmos, invisible to the naked eye but detectable with radio telescopes, carrying encoded fragments of the universe's history. Some pulsars emit not just in radio frequencies but across the entire electromagnetic spectrum, from gamma rays to X-rays. These emissions vary depending on the pulsar's age, environment, and rotation rate. Young pulsars, bursting with energy, often light up in high-energy radiation, while older pulsars emit faint, steady pulses that are like the final echoes of a long cosmic life. Pulsars also serve as celestial signposts, their predictable signals enabling precise navigation in space. Imagine a future where interstellar travelers use pulsars as a cosmic GPS, their regular beats guiding spacecraft through the dark void. In this way, pulsars may one day become our allies in exploring the very universe they help us to understand. But their utility extends beyond navigation. Pulsars have become tools for probing the very fabric of reality. By studying their precise timing, scientists can measure the gravitational effects of massive objects like black holes and detect the faint ripples of gravitational waves. These pulsar timing arrays act as cosmic observatories, monitoring the symphony of spacetime itself. In certain binary systems, where a pulsar orbits another dense star or black hole, the interplay of their gravitational forces offers a rare window into extreme physics. The timing of a pulsar's pulses changes as its orbit is affected by relativistic effects, providing experimental proof of Einstein's theories. These systems are like laboratories for the cosmos, offering insights into phenomena that cannot be recreated on Earth. The most extreme pulsars push the boundaries of what we can comprehend. Magnetars, a rare type of neutron star, possess magnetic fields so intense that they can distort atomic structures and create bursts of energy capable of disrupting satellites and electronics from thousands of light-years away. These cosmic titans remind us of the raw, untamed power that permeates the universe. And yet, for all their intensity, pulsars inspire a profound sense of serenity. Their signals, regular and rhythmic, echo through the vast silence of space, a reminder of the enduring order amidst the chaos of the cosmos. They are both a testament to destruction and a symbol of renewal, born from the ashes of stars but enduring as beacons of stability. As we continue to study pulsars, their mysteries deepen. What lies at the heart of a neutron star? Could the core of these objects harbor forms of matter that defy our current understanding of physics? Do pulsars play a role in the broader mechanisms of galaxy formation and evolution? Each discovery brings us closer to answering these questions, but it also opens new realms of inquiry. Pulsars are not just objects of fascination, they are keys to understanding the universe itself. From the death of stars to the origins of time, from the smallest particles to the largest structures, they connect the vast and the infinitesimal, the known and the unknown. The secrets encoded within pulsars' signals extend beyond astrophysics and reach into the very nature of reality itself. These dense, spinning remnants of once massive stars allow us to glimpse the interplay of forces that govern the cosmos at its most extreme. Take, for instance, the concept of spacequakes, sudden and violent shifts in a pulsar's crust caused by immense magnetic or gravitational forces. These quakes release bursts of energy that ripple outward, momentarily disrupting the pulsar's otherwise perfect rhythm. By studying these disruptions, scientists gain insight into the exotic material that composes neutron stars, a form of matter so dense that it approaches the theoretical limits of compression. The core of a pulsar remains one of the most tantalizing mysteries in astrophysics. Beneath the thin crust lies a world where neutrons are packed together so tightly that they may form superfluid or superconducting states. Some theories suggest that even stranger substances, like quark matter, could exist at the center of these stars, representing the purest and most primordial state of matter ever conceived. As we peer deeper into the nature of pulsars, we also uncover their role as cosmic archivists. The signals from pulsars not only reveal their own properties but also tell us about the space they travel through. When their beams pass through interstellar plasma, they interact with the charged particles in a process known as dispersion. By analyzing how different frequencies of a pulsar's signal arrive at Earth at slightly different times, we can map the density and structure of interstellar matter. Even on a galactic scale, pulsars serve as timekeepers, marking the grand rhythms of cosmic evolution. By observing how their rotations change over time, scientists can detect the subtle tug of gravitational waves, distortions in spacetime caused by the movement of massive objects like merging black holes or orbiting neutron stars. These pulsar timing arrays have become one of the most promising tools for studying the universe's largest-scale phenomena. And then there are the rarest pulsars, those in orbit around other stars, including white dwarfs, neutron stars, or even black holes. In these systems, known as pulsar binaries, the gravitational interactions create a dance of unimaginable precision. The pulses we observe from such systems reveal the tiny variations caused by the bending and stretching of spacetime, offering direct tests of general relativity. The double pulsar system, PSR J0737-3039, discovered in 2003, remains one of the most extraordinary examples of this cosmic choreography. Here, two neutron stars orbit each other in a tight embrace, their beams sweeping past one another as they spiral closer together over millions of years. The insights gleaned from this system have confirmed predictions about gravitational wave emission, showing us how energy is radiated away as these stars lose momentum an inch closer to a final, cataclysmic collision. Pulsars also shed light on the early history of the universe. Some pulsars reside in globular clusters, dense collections of ancient stars that orbit the Milky Way like satellites. These clusters are some of the oldest structures in the galaxy, and the pulsars within them act as fossil records, preserving details about the conditions of the early cosmos. As if this were not enough, pulsars may even help answer one of the most profound questions in physics, the nature of dark matter. Some scientists hypothesize that the precise timing of pulsars could reveal anomalies caused by interactions with dark matter particles or even dark energy. If these tiny fluctuations in timing can be detected, pulsars might hold the key to solving one of the greatest mysteries of the universe. And yet, despite their immense power and importance, pulsars remain silent observers of a universe in motion. They do not demand attention, nor do they reveal their secrets easily. It is through our own curiosity and ingenuity that we have learned to listen to their signals, to decode their rhythms, and to uncover the stories they have to tell. Each discovery leads to more questions. Could pulsars act as natural detectors for the elusive cosmic strings, hypothetical remnants of the Big Bang? Might they someday guide interstellar travelers across the vast, uncharted distances between stars? Could their regular signals be harnessed as universal time standards, uniting civilizations across the galaxy? The possibilities are as endless as the cosmos itself. Beyond their role as timekeepers of the universe, pulsars might be the ultimate navigational aids for future explorers venturing into the vast unknown. Imagine starships sailing across interstellar space, guided not by terrestrial GPS satellites but by the precise beats of pulsars. Each pulsar's unique signal, a cosmic fingerprint, provides a position marker, allowing spacecraft to triangulate their location with extraordinary precision. This concept is not merely science fiction, it is being tested today. NASA's NICER, Neutron Star Interior Composition Explorer, experiment has demonstrated how pulsars can serve as a celestial positioning system. By timing the arrival of X-ray pulses from millisecond pulsars, spacecraft could navigate independently, opening the door to autonomous exploration far beyond our solar system. Pulsars also provide a natural way to communicate across cosmic distances. The precision of their pulses makes them ideal candidates for encoding and transmitting information. Already, humanity has sent messages into space using pulsar maps, like those inscribed on the golden records aboard the Voyager spacecraft. These maps point to Earth's location in the galaxy using the relative positions of pulsars, each identified by its unique frequency and pulse period. Should an intelligent extraterrestrial civilization discover these records, pulsars could act as universal guideposts, enabling them to trace the message back to its origin. But the idea of pulsars as cosmic communicators raises a tantalizing question: could some of their signals be artificial? The discovery of the first pulsar in 1967 briefly led to speculation that the regularity of its signals might indicate an intelligent source. While this was ultimately disproven, the idea lingers, fueled by the notion that any sufficiently advanced civilization might harness the power of pulsars for their own purposes. If an alien civilization were to manipulate the emissions of a pulsar, how would we recognize it? Could we detect subtle anomalies in timing or frequency that deviate from natural patterns? These questions remain unanswered, but they inspire ongoing searches for signals that might hint at advanced technological activity in the universe. Meanwhile, the study of pulsars continues to revolutionize our understanding of fundamental physics. In particular, the discovery of fast radio bursts, FRBs, intense, millisecond-long pulses of radio waves originating from deep space, has opened a new frontier. While not directly linked to pulsars, these mysterious signals share some similarities and may even originate from exotic neutron stars or magnetars. The search for the origins of FRBs parallels our study of pulsars, demonstrating how much remains unknown about the universe's most extreme objects. Could pulsars be the progenitors of these bursts? Or do they represent a completely new class of astrophysical phenomena? As we refine our instruments and methods, we uncover ever finer details about pulsars themselves. Observatories like the Square Kilometre Array, SKA, and next-generation radio telescopes will allow scientists to detect pulsars in other galaxies, vastly expanding our catalog and deepening our knowledge of their distribution and properties. These advancements may help solve enduring mysteries, such as the missing pulsar problem. Theoretical models predict far more pulsars than we have observed. Where are the others? Are they hidden in regions of space shrouded by gas and dust, or do they emit signals too faint or too unusual for us to detect with current technology? Additionally, pulsars could illuminate the cosmic drama of the early universe. The first stars and galaxies likely gave rise to the earliest pulsars, whose remnants may still exist today. By studying ancient pulsars, we might trace the evolution of the universe from its earliest epochs to the formation of modern galaxies. In their ceaseless rotations, pulsars bridge the gap between the infinitesimal and the infinite. They embody extremes of density, gravity, and magnetism while offering insights into the largest scales of cosmic structure. Their signals carry the fingerprints of the forces that govern our universe, from the quantum realm to the vast expanses of intergalactic space. Yet, for all their scientific importance, pulsars also evoke a sense of wonder. Their existence reminds us of the universe's capacity for both destruction and renewal. A star dies in a cataclysmic supernova, but its core endures, transformed into an object of unimaginable density and power. From chaos emerges order, and from destruction, creation. These silent, distant beacons pulse in the dark, their rhythms unchanging across millions of years. They are cosmic reminders that the universe is alive with patterns, with cycles, and with stories waiting to be told. Pulsars are more than just astrophysical curiosities, they are the universe's storytellers, carrying encoded records of cosmic events that span eons. As we continue to unravel their mysteries, we uncover connections to some of the most profound and fundamental questions about our reality. One such question concerns the very fabric of spacetime. Pulsars, with their incredible precision, offer a unique way to detect ripples in spacetime caused by the most massive objects in the cosmos. Gravitational waves, predicted by Einstein's theory of general relativity, are distortions that stretch and compress spacetime as they pass. While these waves were first observed directly in 2015 using laser-based interferometers, pulsars provide a complementary and far-reaching method for studying them. By monitoring a network of pulsars scattered across the galaxy, what scientists call a pulsar timing array, researchers can detect minute changes in the arrival times of their signals. These changes, occurring over years or even decades, indicate the passage of gravitational waves produced by events like the mergers of supermassive black holes. This technique allows us to probe gravitational waves at frequencies inaccessible to other detectors, opening a new window into the dynamics of the universe on colossal scales. But pulsars do not merely observe the universe, they are active participants in its drama. In rare cases, pulsars themselves may contribute to the generation of gravitational waves. When two neutron stars orbit one another in a close binary system, their immense gravitational interactions distort spacetime, radiating energy away in the form of gravitational waves. Over time, this energy loss causes the stars to spiral inward, eventually colliding in a spectacular event known as a kilonova. These collisions are not just dramatic, they are cosmic alchemists. The intense conditions of a kilonova forge heavy elements like gold, platinum, and uranium, scattering them into space to become part of future stars, planets, and even life. The atoms in your jewelry, the uranium powering nuclear reactors, and the gold circuits in your electronics may have been created in the fiery aftermath of a neutron star collision billions of years ago. Pulsars also serve as keys to understanding the enigmatic forces shaping the universe. For instance, the study of their extreme magnetic fields sheds light on one of the most powerful yet least understood phenomena in the cosmos. Magnetars, a type of neutron star with magnetic fields a quadrillion times stronger than Earth's, produce bursts of energy so intense they can briefly outshine entire galaxies. These bursts, known as soft gamma-ray repeaters, are windows into the behavior of matter under conditions that are impossible to replicate in terrestrial laboratories. The existence of such fields challenges our understanding of how magnetic forces operate on cosmic scales. Do magnetars represent a fleeting stage in a neutron star's life, or are they the remnants of a particularly violent birth? By studying these objects, we not only learn about their origins but also gain insights into the complex magnetic interactions that shape galaxies and fuel phenomena like solar winds and star formation. Even the environments surrounding pulsars are rich with information. Pulsar wind nebulae, vast clouds of charged particles accelerated to near-light speeds by a pulsar's magnetic field, illuminate the interstellar medium, acting as natural laboratories for high-energy physics. These glowing remnants offer glimpses into the processes that govern particle acceleration, shedding light on phenomena as diverse as cosmic rays and supernova remnants. And what of pulsars' role in understanding the ultimate fate of the universe? Their signals may provide clues about dark matter, the mysterious substance that makes up roughly 27% of the universe's mass-energy content. If dark matter interacts with pulsars in detectable ways, altering their timing or producing faint signals in their emissions, it could reveal the properties of this elusive material. Some theories even propose that pulsars might serve as tools for investigating the nature of dark energy, the force driving the accelerated expansion of the universe. By measuring how pulsar timing changes over billions of years, we might detect subtle shifts that hint at the influence of this enigmatic force on cosmic scales. As we peer deeper into the pulsar population, we are reminded of their variety and abundance. With each new discovery, whether it be a millisecond pulsar spinning at incomprehensible speeds or a magnetar unleashing bursts of energy, we find another piece of the puzzle that is our universe. Pulsars are not isolated anomalies, they are integral components of the cosmic symphony, each one contributing its unique rhythm to the grand composition of existence. These distant, pulsing stars remind us that the cosmos is a place of extremes, extreme density, extreme energy, extreme beauty. In their relentless rotation, pulsars symbolize the persistence of nature's order amid chaos. They endure through the death of stars, the collision of galaxies, and the vast sweep of time, their signals carrying the essence of the universe itself. And so, as we listen to the pulses of these cosmic timekeepers, we are not merely observing the universe, we are participating in its story. With every beat, pulsars call to us, inviting us to explore, to understand, and to marvel at the infinite wonder of the cosmos. The story of pulsars intertwines with the grandest scales of cosmic history, stretching from the origins of the universe to its possible futures. As timekeepers of the cosmos, their steady pulses bridge epochs, reminding us that even in the vast, cold emptiness of space, there exists a rhythm as ancient as time itself. Consider the early universe, a time of chaos and creation. In the wake of the Big Bang, matter coalesced into stars and galaxies, initiating cycles of birth, death, and rebirth. Pulsars emerged from this crucible, forged in the deaths of the first massive stars. These ancient remnants, some still active today, serve as fossils of a cosmos in its infancy, offering glimpses into the conditions that shaped the galaxies we now call home. As galaxies grew and evolved, pulsars became embedded within their intricate structures. Their immense magnetic fields and high-energy winds influenced their surroundings, stirring the interstellar medium and contributing to the dynamics of star formation. In this way, pulsars played an indirect but crucial role in the enrichment of galaxies with the heavy elements necessary for planets and life. Fast forward to the present, and pulsars continue to illuminate some of the most puzzling aspects of astrophysics. For example, their incredibly precise timing allows us to test the constancy of fundamental forces over time. By comparing the timing of pulsar signals with atomic clocks on Earth, scientists can determine whether physical constants like the speed of light or the strength of gravity have changed over billions of years. Thus far, the evidence suggests an astonishing stability, reinforcing our understanding of the laws that govern the universe. Yet, there are hints that pulsars might also reveal exceptions to these rules. Some theories suggest that under extreme conditions, such as those found in the core of neutron stars, new states of matter or even new forces might emerge. Could pulsars, in their infinite extremes, harbor the keys to unlocking physics beyond the standard model? The potential of pulsars to rewrite our understanding extends even to their youngest cousins. Magnetars, with their short lifespans and explosive behaviors, push the boundaries of what we know about magnetic fields and energy release. The bursts from these objects are so intense that they occasionally reach Earth, offering natural experiments in high-energy astrophysics. One such event, detected in 2004, temporarily altered Earth's ionosphere, highlighting the profound influence these distant objects can exert even across vast distances. Looking to the future, pulsars may help us navigate one of the most ambitious endeavors humanity has ever conceived, the search for life beyond Earth. Their signals, traveling undisturbed across interstellar space, act as pristine markers that can guide probes and telescopes toward promising regions of the galaxy. For instance, some pulsars are located near the galactic habitable zone, a region thought to be particularly favorable for the development of life. By studying these pulsars and their surroundings, we might identify planets or systems that could harbor the conditions necessary for biology to thrive. Even more provocatively, pulsars could serve as benchmarks in the search for technosignatures, indicators of advanced extraterrestrial civilizations. The regularity of pulsar signals makes them ideal for detecting anomalies, such as artificial modulations or unusual frequencies. If an intelligent civilization were to manipulate a pulsar's emissions to send a message, would we recognize it? As we contemplate these possibilities, the vastness of time becomes a central theme. Pulsars endure for millions to billions of years, outlasting the lifespans of stars and planets. They are cosmic sentinels, observing the slow dance of galaxies and the imperceptible shifts in the structure of the universe. Their longevity makes them unique witnesses to cosmic events that unfold on incomprehensible timescales. The merging of supermassive black holes, the formation of new galaxies, the drift of interstellar matter, all of these processes occur against the steady backdrop of pulsar signals, which serve as unchanging reference points in a dynamic universe. One cannot help but marvel at the duality of pulsars. On the one hand, they are the remnants of violence, born in the explosive deaths of stars. On the other, they embody order, precision, and continuity, pulsing in perfect synchrony for eons. They are both destroyers and creators, chaotic and serene. And while pulsars have been studied for decades, their full story is far from complete. With each new technological advance, we gain the ability to observe them in greater detail, detect more distant examples, and uncover subtler variations in their behavior. The future holds promises of discoveries that could change not only how we see pulsars but how we see the universe itself. What lies ahead for these cosmic lighthouses? Will they continue to act as timekeepers for a universe that is cooling, expanding, and evolving? Could they eventually fade into silence, leaving behind only echoes of their existence? Or will they, in some way we cannot yet imagine, influence the fate of the cosmos itself? The answers may not come in our lifetimes. But the questions themselves remind us of the profound connection we share with the universe. Pulsars are not just distant objects in the night sky, they are part of the grand tapestry that defines our reality. And as we continue to listen to their signals, decode their rhythms, and study their stories, we are drawn deeper into the cosmic mystery. For in their pulses lies not just the story of stars, but the story of everything. The story of pulsars continues to expand, reaching into realms of science and philosophy that stretch the limits of human understanding. These celestial clocks, beating across the vast expanse of time, carry with them profound implications about the nature of existence, the structure of the cosmos, and humanity's place within it. As we explore pulsars further, one of the most intriguing possibilities arises in the realm of quantum mechanics. The extreme conditions inside neutron stars, with matter compressed to densities that exceed the atomic nucleus, create a laboratory for testing the quantum laws that govern the smallest scales of reality. Some theories propose that the cores of neutron stars may collapse into strange matter, composed of particles called strange quarks. This state of matter, if it exists, would represent a phase of the universe that might have been common shortly after the Big Bang. Pulsars could be the remnants of a primordial era, holding within them clues to the birth of the cosmos. Moreover, the interaction of a pulsar's immense gravity with spacetime itself offers an avenue to explore quantum gravity, the elusive theory that seeks to unite Einstein's general relativity with quantum mechanics. In binary systems where pulsars orbit black holes, the gravitational effects are so extreme that they could reveal new insights into the nature of spacetime. But pulsars are not just windows into the distant past, they also point toward the future of cosmic evolution. In the far reaches of the galaxy, pulsars play a critical role in the dynamic processes that shape star clusters, nebulae, and even entire galactic structures. Their energy outputs, from winds of high-energy particles to their intense magnetic fields, drive phenomena that influence the distribution of matter and energy across the Milky Way. For example, the Crab pulsar, located at the heart of the Crab Nebula, is a striking example of how a single pulsar can energize its surroundings. The nebula's intricate filaments and glowing plasma are powered by the pulsar's rotational energy, creating a breathtaking reminder of the interplay between stars and their environments. On even larger scales, pulsars contribute to the ongoing cycle of matter in the universe. When a pulsar finally exhausts its energy and fades into silence, its remnants, the heavy elements forged in its violent birth, become part of the interstellar medium. These materials are eventually incorporated into new generations of stars and planets, ensuring that the universe remains a place of constant renewal. This connection between pulsars and the cosmic cycle raises another profound question: could pulsars play a role in the formation of life itself? The elements that make up our bodies, carbon, oxygen, nitrogen, and others, were forged in the hearts of stars and distributed across the galaxy by supernova explosions. Pulsars, as remnants of these processes, are inextricably linked to the conditions that allow life to exist. Even as we ponder the biological implications of pulsars, their philosophical impact cannot be ignored. They remind us of the immensity of time and space, of processes so vast and enduring that they challenge our ability to comprehend them. A pulsar's lifespan, millions to billions of years, dwarfs the brief moment of human existence, placing our lives in the context of the universe's endless unfolding. Yet, despite this cosmic scale, pulsars also connect us to something deeply personal. Their regularity and persistence evoke a sense of order, a reassurance that even in the chaos of creation and destruction, there are constants that endure. Their signals, though emitted from the depths of space, feel almost intimate, as if the universe itself is speaking to us, reminding us of our shared origins. The exploration of pulsars is far from over. As new technologies emerge, we will uncover pulsars in distant galaxies, observe their interactions with other extreme objects, and perhaps even detect phenomena we cannot yet imagine. Future telescopes, like the Square Kilometre Array, will allow us to map the galaxy in unprecedented detail, revealing new populations of pulsars and expanding our understanding of their role in the cosmos. And there may yet be surprises. Could pulsars exhibit behaviors we have never seen? Might they harbor unknown forms of matter or energy? Could they help us answer the deepest questions about the universe, from the nature of dark matter to the fate of time itself? Pulsars are not just objects of study, they are invitations to wonder, to curiosity, to exploration. They remind us that the universe is not static but dynamic, a place of endless mystery and discovery. As their signals traverse the vast distances of space, they carry with them more than just information. They carry stories of stars, of galaxies, of forces that shape the cosmos, and of the human spirit, which seeks to understand it all. And so, as we listen to the steady rhythms of these cosmic lighthouses, we are reminded of something profound, that we are part of this grand story, woven into the fabric of a universe that is as vast as it is beautiful. The study of pulsars not only deepens our understanding of the universe but also challenges the limits of our imagination. These enigmatic objects, spinning ceaselessly in the cold expanse of space, invite us to think beyond the confines of Earth, beyond the immediacy of human experience, and into the vast continuum of time and space. As we refine our ability to detect and analyze pulsars, we are beginning to ask new questions that could redefine our place in the cosmos. For example, could pulsars serve as a benchmark for measuring the universe's expansion? The precision of their timing allows us to detect even the faintest perturbations in spacetime. If these signals could be used to trace the movement of galaxies relative to one another, they might offer a new way to measure the influence of dark energy on the large-scale structure of the universe. Even more intriguingly, pulsars could help us understand the ultimate fate of the cosmos. If the universe is expanding, as current observations suggest, will it continue to do so forever? Or will it eventually contract, reversing its trajectory in a big crunch? Pulsars, as cosmic timekeepers, might hold clues within their timing and distribution, offering evidence about the interplay between gravity, dark energy, and the fabric of spacetime. Yet, the questions pulsars pose extend beyond the physical. They challenge us to reconsider how we perceive time itself. A pulsar's pulse represents an unerring rhythm, repeating over millions of years, unaltered by the chaos and entropy surrounding it. For civilizations, both human and hypothetical, pulsars could provide an eternal framework, a constant reference point against which the fleeting moments of life gain perspective. Imagine a future where pulsars are woven into the fabric of human culture. In a galaxy-spanning civilization, pulsars could replace atomic clocks as the standard for timekeeping, uniting distant planets and colonies under a universal clock that transcends the limitations of individual worlds. Their signals, beaming across light years, would serve as a reminder of our shared origins and the vastness of the cosmos we inhabit. The role of pulsars in navigation may also evolve into something far beyond current applications. Already, the concept of pulsar-based navigation, or XNAV, has demonstrated the feasibility of using pulsars as galactic waypoints. For explorers venturing into interstellar space, pulsars would serve as unerring guides, allowing spacecraft to pinpoint their location anywhere in the galaxy. This concept, born of science fiction, is becoming science fact, with potential to revolutionize our approach to space travel. But pulsars may offer even more. Their precision and regularity could act as a form of communication across vast cosmic distances. In a universe where direct communication between civilizations is limited by the speed of light, pulsars might serve as intermediaries, their signals modulated to carry messages that could endure for eons. Could pulsars become a kind of universal post office, facilitating the exchange of knowledge across the stars? While this notion remains speculative, it underscores a fundamental truth about pulsars: they are both objects of study and sources of endless inspiration. Their presence in the universe challenges us to think not only about what is but also about what could be. And still, there are pulsars we have yet to find. Hidden in the dense cores of globular clusters, shrouded by interstellar dust, or too faint to detect with current technology, these unseen pulsars may hold answers to questions we haven't yet thought to ask. They may reveal new phenomena, new forms of matter, or new laws of physics that push the boundaries of what we know. One of the most tantalizing possibilities is the existence of pulsars beyond our galaxy. While we have detected extragalactic pulsars, they remain rare, their signals often drowned out by the noise of intergalactic space. As our instruments grow more sensitive, we may uncover pulsars in distant galaxies, their signals carrying information about the large-scale structure of the universe and the processes that govern galaxy formation. In the distant future, as the universe continues to expand and cool, pulsars may represent one of the last beacons of activity in a fading cosmos. Long after stars have burned out and galaxies have dispersed, the faint pulses of neutron stars may endure, their rhythms echoing through the dark void. These final pulsars, spinning slowly in a universe approaching thermal equilibrium, would be reminders of the fiery births that once defined cosmic history. They would pulse on, bearing silent witness to the ultimate fate of all things, even as the cosmos itself drifts toward stillness. Pulsars, in their quiet persistence, encapsulate the paradox of the universe: they are at once fleeting and eternal, chaotic and ordered, violent and serene. They are a reflection of the cosmos itself, infinite in complexity, boundless in beauty, and always full of surprises. And as we continue to study them, to decode their messages and uncover their secrets, we are reminded that the journey of discovery is as infinite as the universe. Pulsars teach us that even in the deepest darkness, there is light, even in the vast silence, there is a pulse. And that pulse, echoing across the ages, reminds us that we are connected to the stars, to the cosmos, and to the endless story of existence. The future of pulsar research is as boundless as the universe they inhabit. With every technological advance, we edge closer to uncovering the deeper truths hidden within these spinning remnants of stars. Yet, the more we learn, the more profound the questions become, touching on the very essence of what it means to exist in a universe as vast and complex as our own. One of the most exciting frontiers lies in the discovery and study of the elusive nanohertz gravitational waves, the faint, low-frequency ripples in spacetime generated by the movement of supermassive black holes as they orbit one another. These waves stretch and compress the distances between pulsars and Earth in imperceptibly small amounts, detectable only through the meticulous timing of pulsar signals. The International Pulsar Timing Array, PDA, collaborations are at the forefront of this effort. By monitoring a network of millisecond pulsars across the sky, PDAs aim to map these faint gravitational echoes, revealing the cosmic symphony of merging black holes scattered throughout the universe. The detection of these waves will open a new chapter in gravitational wave astronomy, offering insight into the formation and evolution of galaxies over billions of years. Meanwhile, the Square Kilometre Array, SKA, an ambitious next-generation radio telescope currently under development, promises to revolutionize our ability to detect and study pulsars. The SKA will dramatically increase the number of known pulsars, including those in distant galaxies, and provide unparalleled precision in timing measurements. This will enhance our ability to probe the extreme physics of neutron stars and detect subtle deviations that could point to new laws of nature. Beyond these scientific milestones, pulsars may also help us address questions about the very origins of the universe. Some pulsars, born in the early epochs of cosmic history, could still be active, their signals carrying information about conditions in the primordial universe. These ancient timekeepers could provide clues about the distribution of matter and energy shortly after the Big Bang, helping us refine our understanding of how galaxies and cosmic structures came to be. Pulsars are also key to testing fundamental principles of physics, such as the universality of free fall, the idea that all objects, regardless of their composition, fall at the same rate in a gravitational field. By studying binary pulsar systems where one object is a neutron star and the other a white dwarf, scientists can test whether these exotic objects obey the same gravitational rules as ordinary matter. Any deviation from the expected results could point to new physics, perhaps even a unified theory of gravity and quantum mechanics. The search for new pulsar types is another exciting frontier. Exotic systems, such as pulsar black hole binaries, remain theoretical but could provide unparalleled laboratories for testing general relativity in extreme conditions. The detection of such a system would allow scientists to study the interaction between a pulsar's intense magnetic field and a black hole's event horizon, shedding light on the mysterious boundary between matter and energy. In addition to their scientific value, pulsars have a unique cultural and philosophical significance. They remind us of the enduring nature of cosmic processes, their ceaseless pulses echoing through the eons. For future generations, pulsars may serve as a metaphor for resilience and continuity, symbols of the enduring rhythms that persist even in the face of unimaginable forces. In the distant future, when humanity has ventured far beyond the confines of Earth, pulsars may become an integral part of our interstellar lives. Their precise signals could form the backbone of a galactic communications network, enabling distant civilizations to exchange information across vast distances. They may also inspire art, literature, and music, their rhythms serving as a universal language that transcends cultural and temporal boundaries. Even as we project into the future, pulsars connect us to the past. The heavy elements that make up our bodies, forged in the supernovae that gave birth to pulsars, tie us to the life cycle of stars. In this sense, pulsars are not just distant objects in the night sky, they are part of us, reminders of our shared origins and our place in the cosmos. As we listen to their signals, we are reminded of the delicate balance between chaos and order that defines the universe. Pulsars are born in the most violent events imaginable, yet they emerge as beacons of stability, their pulses marking the passage of time with unerring precision. They are a paradox, embodying both destruction and creation, silence and sound, chaos and harmony. Their existence challenges us to think beyond the boundaries of what we know, to embrace the mystery and wonder that lies at the heart of the cosmos. Pulsars remind us that the universe is not just a collection of objects but a living, dynamic entity, filled with rhythms and patterns that resonate across space and time. And so, as we continue to study these enigmatic beacons, we are not merely exploring the universe, we are exploring ourselves, our place in the grand tapestry of existence, and the infinite possibilities that lie ahead. The story of pulsars is far from over. With every new discovery, every new insight, we come closer to understanding the profound truths they hold. But perhaps the greatest lesson pulsars teach us is that the journey itself, the act of listening, observing, and wondering, is the true measure of our connection to the cosmos. The deeper we venture into the mysteries of pulsars, the more we realize their unparalleled significance in shaping our understanding of the universe. These ancient remnants of stellar death are more than just cosmic phenomena, they are messengers, bridging the past, present, and future in ways that challenge the boundaries of human knowledge and imagination. One of the most tantalizing questions about pulsars is their role in uncovering the origins of cosmic magnetism. The universe is filled with magnetic fields, from the subtle pull that guides a compass on Earth to the colossal fields threading entire galaxies. Yet the origin of these magnetic fields remains one of astrophysics' enduring enigmas. Pulsars, with their unimaginably strong magnetic fields, may hold the key. The magnetic fields of pulsars can reach strengths of up to 101510 carat 1015 Gauss, billions of times stronger than the most powerful magnetic fields we can generate on Earth. How these fields form, and how they evolve over time, is a question that touches on the fundamental properties of matter and energy. Studying pulsars allows scientists to trace the life cycle of magnetic fields, from their birth in supernovae to their gradual decay over millions of years. These magnetic fields also play a central role in the emission of pulsar beams. As charged particles spiral along magnetic field lines near a pulsar surface, they accelerate to nearly the speed of light, emitting radiation across the electromagnetic spectrum. This process, though well understood in principle, raises deeper questions about the interplay between matter, energy, and spacetime in extreme conditions. But pulsars are not just probes of magnetic phenomena. They are also uniquely suited to test the limits of Einstein's general relativity. In systems where pulsars orbit close to massive companions, such as other neutron stars or black holes, the gravitational forces are so intense that spacetime itself is warped and twisted. These systems allow scientists to measure effects like gravitational redshift and time dilation with unparalleled precision, providing some of the strongest evidence yet for the validity of relativity. One of the most remarkable examples of this is the Hulse-Taylor binary pulsar, discovered in 1974. This system, consisting of two neutron stars in a close orbit, provided the first indirect evidence for the existence of gravitational waves. The gradual decay of the orbit, caused by the emission of gravitational waves, matched predictions from Einstein's equations with stunning accuracy. Today, this discovery stands as a cornerstone of modern astrophysics and a testament to the power of pulsar science. As we look to the future, the study of pulsars may help us answer even more fundamental questions about the nature of the universe. For instance, could pulsars be used to measure the mass of neutrinos, the elusive particles that permeate the cosmos but interact with matter only weakly? Neutrinos, though nearly massless, have a profound influence on the evolution of the universe, and their properties remain one of the greatest mysteries in physics. By analyzing how pulsar signals are affected by neutrino interactions, scientists might finally pin down their mass and role in cosmic history. Pulsars could also provide insight into the nature of dark matter. If dark matter particles interact with pulsars in subtle ways, they might leave detectable imprints on the timing of their signals. Such deviations, though incredibly faint, could reveal the properties of dark matter and help us understand its influence on the formation of galaxies and the large-scale structure of the universe. As we refine our understanding of pulsars, we also open the door to new technological possibilities. The precision of pulsar timing offers a model for advances in communication and computation, inspiring technologies that rely on the manipulation of signals with extraordinary accuracy. The lessons we learn from pulsars may one day lead to breakthroughs in quantum computing, timekeeping, and even interstellar communication. Yet for all their scientific and technological importance, pulsars are also deeply poetic. Their rhythmic pulses, traversing the vastness of space, evoke a sense of timelessness and continuity. They remind us of the beauty and order that underlies the chaos of the cosmos, a beauty that transcends human understanding and invites us to contemplate the infinite. Pulsars are not just objects of study, they are symbols of the interconnectedness of all things. The atoms in our bodies were forged in the same cosmic furnaces that gave birth to pulsars. The light we see from these distant stars has traveled across the universe, passing through the same space that our planet now occupies. In this way, pulsars remind us that we are part of a vast and ancient story, one that stretches back to the beginning of time and extends far into the future. And so, as we continue to listen to the silent music of the cosmos, marked by the steady beats of pulsars, we are drawn ever closer to the heart of the universe. Their signals, both scientific and symbolic, speak to our deepest questions about existence, purpose, and the nature of reality. Pulsars, in their quiet persistence, teach us that even in the darkest corners of space, there is light. Even in the vast silence, there is rhythm. And even in the face of unimaginable scales, there is a connection that binds us to the stars and to the cosmos itself. The journey of discovery is far from over. Pulsars will continue to guide us, inspire us, and challenge us to think beyond the boundaries of what we know. For in their pulses lies the story of the universe, a story that is still being written, and one that we are privileged to be a part of. Pulsars, with their enigmatic nature and ceaseless signals, serve as reminders that the universe is both infinitely complex and deeply interconnected. Their pulses, originating from distant corners of the cosmos, form a kind of universal heartbeat, a rhythm that connects us to events both ancient and ongoing. Yet, for all their regularity, pulsars also offer surprises, mysteries that challenge our understanding and push the boundaries of science. One such mystery lies in the unexpected behaviors of glitching pulsars. These are pulsars that, despite their otherwise clock-like precision, occasionally experience sudden, brief increases in rotational speed. These glitches, thought to be caused by shifts in the interior structure of the neutron star, reveal the hidden dynamics of matter under extreme conditions. As the outer crust of the pulsar cracks or adjusts under immense stress, angular momentum is redistributed, momentarily altering the star's rotation. Studying these glitches gives scientists a rare glimpse into the inner workings of neutron stars, providing clues about their composition and structure. Do neutron stars have solid cores? Are their interiors composed of superfluid neutrons or even quark matter? Each glitch is a window into a realm of physics that is inaccessible on Earth, allowing us to probe the behavior of matter at densities billions of times greater than water. Equally fascinating are nulling pulsars, which periodically cease emitting detectable radiation before resuming their regular pulses. The reasons for this silence remain unclear, but they hint at complexities in a pulsar's magnetic field or energy generation processes. These interruptions, though frustrating for astronomers, remind us that pulsars are dynamic and evolving, not static machines but living participants in the cosmic drama. Even among pulsars, there are outliers that defy categorization. Magnetars, with their incredible magnetic fields, emit powerful bursts of X-rays and gamma rays that can briefly outshine entire galaxies. Rotating radio transients, RATs, are pulsars that emit sporadic bursts of radio waves, their irregular signals raising questions about how they generate their emissions. These exotic objects, while rare, expand our understanding of the diverse ways in which neutron stars interact with their environments. One of the most intriguing aspects of pulsars is their potential connection to fast radio bursts, FRBs. These mysterious, millisecond-long flashes of radio waves have captivated astronomers since their discovery in 2007. While the origins of FRBs remain uncertain, some theories suggest they may be linked to young, highly magnetized neutron stars. Could pulsars or magnetars be the progenitors of these fleeting but powerful events? If so, what mechanisms could produce such immense bursts of energy? As we delve deeper into these questions, new technologies are enabling discoveries that would have been unimaginable just a few decades ago. The upcoming Square Kilometre Array, SKA, promises to revolutionize our ability to detect and study pulsars, allowing us to identify thousands of new examples, including those in other galaxies. This expanded dataset will offer unparalleled opportunities to test theories about neutron star evolution, magnetic field dynamics, and the role of pulsars in galactic ecosystems. But the significance of pulsars extends beyond the boundaries of astrophysics. They inspire a sense of wonder and curiosity, reminding us of our shared connection to the cosmos. The atoms in a pulsar's core, forged in the fiery heart of a star, are the same atoms that make up the air we breathe, the ground we walk on, and the blood in our veins. In studying pulsars, we are, in a sense, studying ourselves, our origins, our place in the universe, and our future. Imagine a time, perhaps millions of years from now, when humanity or its descendants travel freely among the stars. Pulsars, with their ceaseless rhythms, will guide these explorers, providing a cosmic map that transcends the limitations of time and distance. Their signals, unchanging across millennia, will act as beacons, reminding travelers of their shared origins and the interconnectedness of all things. In this future, pulsars may become more than navigational tools or scientific curiosities. They could serve as cultural touchstones, symbols of endurance and stability in an ever-changing universe. Their pulses might inspire art, music, and philosophy, becoming a universal language that unites civilizations across the galaxy. Yet, even as we look to the future, pulsars ground us in the present. They remind us of the beauty and complexity of the cosmos, of the forces that shape our existence, and of the mysteries that remain to be explored. Their signals, traveling across vast distances, carry with them a message, that the universe is alive with patterns, rhythms, and stories waiting to be uncovered. As we continue to study these remarkable objects, we are reminded of the power of curiosity and the human drive to understand. Pulsars are more than just objects of scientific inquiry, they are symbols of our quest for knowledge, our connection to the cosmos, and our place in a universe that is as mysterious as it is magnificent. And so, the pulses of these distant stars echo on, carrying the story of the universe into the infinite. Each signal, a whisper from the depths of space, invites us to listen, to learn, and to marvel at the grandeur of the cosmos. The rhythmic pulses of neutron stars, born from the deaths of massive stars, represent more than the ticking of cosmic clocks. They symbolize resilience in the face of unimaginable forces and the harmony that emerges from chaos. As we listen to their signals and decode their secrets, we uncover layers of complexity that deepen our understanding of the universe, and ourselves. Among the most captivating recent developments is the study of binary pulsar systems, particularly those involving neutron stars and black holes. These rare pairings offer unparalleled opportunities to study the interplay between the strongest gravitational fields and the most compact forms of matter. When a pulsar orbits a black hole, the curvature of spacetime is extreme, and the pulsar's precisely timed signals are distorted by gravitational effects. By studying these distortions, scientists can test general relativity under conditions that could reveal subtle deviations or entirely new physics. Such systems may also illuminate the mysterious phenomenon of black hole spin. The rotation of a black hole can drag spacetime itself in a process called frame dragging. By analyzing how a pulsar's signal is affected by this spacetime warping, astronomers could measure the black hole's spin and gain new insights into how these enigmatic objects evolve and interact with their surroundings. Even beyond binary systems, pulsars continue to defy expectations. Consider the discovery of planetary pulsars surrounded by exoplanets. One of the first such systems, PSRB 1257+12, revealed planets orbiting a pulsar in an environment bathed in intense radiation. How these planets formed and survived such hostile conditions remains a profound mystery. Their existence challenges our understanding of planetary formation and raises questions about whether life, in some extreme form, could exist in these unearthly environments. Pulsars also intersect with one of the most profound questions in cosmology, the search for extraterrestrial intelligence, SETI. Their precise signals, so regular they were once mistaken for artificial transmissions, could theoretically be used by advanced civilizations as interstellar beacons. While no evidence of alien manipulation has been found, pulsars' suitability as natural galactic lighthouses inspires both scientific inquiry and speculative thought. Could the patterns of their emissions encode messages we have yet to recognize? And yet, even as we imagine distant possibilities, pulsars remain vital tools for understanding the most immediate aspects of the universe's structure. Their signals provide a way to measure the interstellar medium, the vast expanse of gas, plasma, and magnetic fields that fills the space between stars. By analyzing how pulsar signals are delayed and dispersed as they travel through this medium, astronomers can map the density, composition, and movement of interstellar material. This in turn sheds light on processes like star formation and galactic evolution. On a larger scale, pulsars serve as probes of the Milky Way's shape and motion. Their distribution, timing, and velocities reveal the dynamic history of our galaxy, including the gravitational influences of unseen forces like dark matter. By studying pulsars in the outer reaches of the Milky Way and in its satellite galaxies, astronomers can trace the structure of these systems and the invisible halos of dark matter that surround them. Perhaps the most poignant aspect of pulsars is their connection to the concept of cosmic time. Unlike the fleeting events of human history, the lifespans of pulsars stretch across epochs, bridging the gap between the universe's violent past and its uncertain future. In a cosmos destined to expand and cool, pulsars may endure as one of the last sources of activity, their pulses marking the passage of time in an otherwise silent void. As the universe ages, neutron stars will slow their rotation, their magnetic fields will weaken, and their pulses will fade. But even in this eventual quiet, they will leave behind echoes of their existence, frozen remnants of a time when the cosmos was vibrant and alive. These black dwarfs, the ultimate fates of neutron stars, will drift through the darkened universe as monuments to the stars that once were. Yet, even in this seemingly inevitable stillness, there is a kind of beauty. The story of pulsars, like the story of the universe itself, is one of transformation. From the fiery death of a star emerges a beacon of light and rhythm. From destruction comes creation. From silence comes a pulse. And so, as we continue to study these enigmatic objects, we are reminded that the universe is not static but dynamic, a place of endless cycles, where each end is a new beginning. Pulsars, in their enduring rhythms, teach us to look beyond the present moment, to see the cosmos not as a collection of isolated phenomena but as a vast, interconnected whole. Their signals, traveling across millions of light-years, are more than just echoes of the past. They are calls to exploration, to curiosity, and to wonder. They remind us that the cosmos, for all its vastness, is not indifferent. It is alive with patterns, with music, with meaning. In the ceaseless rhythms of pulsars, we find the heartbeat of the universe, a reminder that, even in the infinite expanse of space, we are connected to something greater, something timeless. And so, the story of pulsars continues, as infinite and enduring as the stars themselves. The story of pulsars stretches ever outward, mirroring the boundless expanse of the universe itself. These spinning remnants of stars serve as bridges between the infinitely small and the unimaginably vast, uniting the forces that govern the cosmos with the mysteries that lie at the edge of human understanding. Their steady signals, like the tolling of a distant bell, beckon us to explore further, to ask deeper questions, and to contemplate our place in the grand cosmic dance. One of the most profound aspects of pulsars is their potential to reveal the fundamental nature of spacetime itself. While general relativity has stood as a cornerstone of modern physics for over a century, pulsars provide a way to test this theory under conditions far more extreme than anything experienced on Earth. In particular, systems like the double pulsar, where two neutron stars orbit each other in a tight, relativistic dance, allow scientists to observe phenomena like the precession of orbits and the emission of gravitational waves in real time. These systems act as natural laboratories for exploring how spacetime behaves in the presence of ultradense matter and intense gravitational fields. The precision with which we can measure pulsar signals has already confirmed predictions made by Einstein's equations to an astonishing degree of accuracy. But the possibility remains that subtle deviations could one day point us toward a deeper understanding of gravity, perhaps even a unified theory that links it with quantum mechanics. Beyond testing the known laws of physics, pulsars also hold the potential to uncover entirely new phenomena. One of the most tantalizing ideas involves the search for cosmic strings, hypothetical one-dimensional defects in spacetime that may have formed during the early moments of the universe. If these strings exist, their interactions could create disturbances detectable in pulsar timing, offering a glimpse into the primordial conditions of the cosmos. Meanwhile, the role of pulsars as cosmic timekeepers continues to expand. In addition to their use in pulsar timing arrays to detect gravitational waves, these stellar clocks may one day become the backbone of an interstellar navigation system. As humanity ventures beyond the confines of our solar system, pulsars could serve as universal reference points, enabling spacecraft to determine their precise location and trajectory anywhere in the galaxy. The idea of a galactic positioning system, built on the pulses of these distant stars, represents a profound merging of human ingenuity with the natural rhythms of the universe. This potential for pulsars to guide us physically mirrors their role as guides in our quest for understanding. Their signals, carrying imprints of the interstellar medium, reveal the structure and dynamics of our galaxy. By analyzing how pulsar emissions are scattered, delayed, or refracted as they pass through clouds of gas and plasma, astronomers can map the distribution of matter in unprecedented detail. This, in turn, sheds light on processes like star formation, the behavior of galactic magnetic fields, and the life cycle of interstellar clouds. On even larger scales, pulsars serve as probes of dark matter and dark energy, the mysterious forces that together account for most of the universe's mass-energy content. If dark matter particles interact with pulsars, they might produce detectable anomalies in their timing or emissions. Similarly, long-term monitoring of pulsar timing could reveal how dark energy influences the expansion of the universe, offering clues about its ultimate fate. Yet, for all their scientific significance, pulsars are also deeply symbolic. They embody the duality of the cosmos. Born from the fiery deaths of stars, they emerge as beacons of stability, their pulses enduring across eons. They remind us of the interplay between chaos and order, destruction and creation, that defines the universe on every scale. This symbolism resonates not just in science but in art, philosophy, and culture. Pulsars, with their ceaseless rhythms, have inspired poetry and music, their steady beats reflecting the rhythms of life itself. Their existence challenges us to think beyond the immediate, to consider the vastness of time and space, and to recognize the interconnectedness of all things. Imagine, for a moment, the distant future. Long after humanity has left its cradle, after the stars of our galaxy have begun to fade, pulsars will remain, their signals continuing to mark the passage of time. For civilizations that arise in that distant epoch, these stellar remnants may serve as the last echoes of a vibrant universe, reminders of the stars that once shone brightly in the cosmos. And yet, even as the universe approaches its distant destiny, pulsars will leave behind a legacy. Their pulses, encoded with the history of the cosmos, will endure as faint whispers in the void, carrying stories of creation, transformation, and endurance. In their quiet persistence, pulsars teach us that the universe, for all its vastness and mystery, is not indifferent. It is alive with rhythms, patterns, and connections that speak to the fundamental unity of existence. And as we continue to study these remarkable objects, we are reminded that the act of discovery is itself an affirmation of our place in this grand cosmic story. The pulses of these distant stars echo across time and space, reminding us that, even in the vast silence of the universe, there is music. Even in the darkness, there is light. And even in the infinite, there is meaning. And so, the journey continues, a journey of listening, learning, and marveling at the infinite wonders of the cosmos. The story of pulsars is not just the story of stars, it is the story of existence, a story that we are privileged to be a part of, and one that will continue to unfold for as long as the universe itself endures. The narrative of pulsars extends like a thread woven through the very fabric of the cosmos, linking the violence of stellar death to the profound order of their rhythmic pulses. As our understanding deepens, these enigmatic objects offer increasingly profound insights into the structure, evolution, and ultimate fate of the universe. Among the most striking aspects of pulsar research is their ability to act as cosmic beacons, mapping regions of space that are otherwise invisible to us. For example, pulsar timing arrays have already begun to detect the subtle tug of gravitational waves rippling through the universe. These signals, caused by the movements of supermassive black holes in distant galaxies, allow us to eavesdrop on processes that occur over millions or even billions of years. But this is only the beginning. Future generations of telescopes and computational tools promise to refine these observations, revealing a tapestry of gravitational waves at different frequencies. This gravitational wave background, like the cosmic microwave background that reveals the remnants of the Big Bang, will provide a record of the universe's dynamic history. Pulsars, as precise timers scattered throughout the galaxy, will be the key to unlocking this information. Beyond their role in gravitational wave detection, pulsars are expanding our understanding of fundamental physics. In particular, the search for neutron stars that exceed the so-called Tolman-Oppenheimer-Fokoff limit, the theoretical maximum mass of a neutron star, may provide clues about what happens when matter is compressed to its absolute limit. Such discoveries could point to the existence of quark stars, exotic objects even denser than neutron stars, where matter dissolves into its most fundamental constituents. Pulsars also continue to surprise us with their diversity. Some pulsars exhibit behaviors that defy classification, such as those in binary systems with white dwarfs or black holes. These pairings reveal extreme astrophysical phenomena, from the tidal disruption of stellar material to the formation of relativistic jets. Each new discovery adds another piece to the puzzle, expanding our understanding of how stars evolve, interact, and ultimately die. One particularly fascinating phenomenon is the interaction between pulsars and their surrounding environments. Pulsar wind nebulae, for example, are vast regions of high-energy particles accelerated by the pulsar's magnetic field. These nebulae glow across the electromagnetic spectrum, from radio waves to X-rays, and provide insights into the processes that drive cosmic particle acceleration. In studying these systems, we are not only learning about pulsars themselves but also gaining clues about phenomena like cosmic rays, which permeate the universe and even affect Earth. The interplay between pulsars and their environments extends to their relationships with other stars. Millisecond pulsars, for example, often acquire their rapid spins by stealing material from a companion star in a binary system. This process, known as accretion, transfers angular momentum to the neutron star, spinning it up to incredible speeds. These systems, in turn, help us understand the dynamics of stellar evolution, binary interactions, and the conditions that lead to the formation of exotic objects like black holes and magnetars. And what of the future? As our technology advances, we will uncover new populations of pulsars, including those in regions of the universe previously hidden from us. Pulsars in globular clusters, for example, offer insights into the dense environments of these ancient star systems, while pulsars near the galactic center provide a unique view of the supermassive black hole that anchors the Milky Way. Pulsars may also play a role in humanity's long-term survival. As we look to the stars for resources, knowledge, and even new homes, pulsars could serve as navigational aids, guiding us through the vastness of space. Their regular signals, unaffected by the passage of time or the chaos of stellar environments, offer a stability that transcends the limitations of human-made systems. But pulsars are more than tools for exploration, they are windows into the soul of the universe. Their existence challenges us to think beyond the here and now, to consider the forces that shape the cosmos and our place within it. They remind us that the universe is not static but alive with rhythms, cycles, and transformations that echo across the ages. Imagine a time billions of years from now, when the stars in the night sky have faded, their light replaced by the faint glow of distant galaxies. In this far future, pulsars may remain as the last beacons of a once vibrant cosmos. Their pulses, steady and unyielding, will continue to mark the passage of time, serving as monuments to the universe's boundless creativity and enduring beauty. And so, the story of pulsars is not just a story of stars but a story of connection. They link the smallest particles to the largest structures, the fleeting moments of human existence to the vast sweep of cosmic time. They remind us that even in the darkest corners of space, there is light, and even in the silence, there is music. As we listen to their signals, we are reminded of the infinite possibilities that lie before us. Pulsars, in their quiet persistence, call us to explore, to learn, and to marvel at the wonders of the cosmos. Their pulses, traveling across the vast distances of space and time, carry a message, that the universe is alive with stories waiting to be told, and that we are a part of this grand, unfolding narrative. The story of pulsars continues to unfold like a vast cosmic symphony, with each discovery adding new notes to an ever-expanding melody. Their relentless pulses, traveling across unimaginable distances, are more than mere markers of time, they are whispers from the universe, carrying with them the echoes of creation and the promise of knowledge yet to be uncovered. One of the most fascinating aspects of pulsar research lies in its connection to the early universe. Some pulsars are so ancient that their formation occurred shortly after the first stars began to burn. These relics are time capsules, their signals carrying imprints of the conditions that existed when the cosmos was young. By studying them, we gain insight into the processes that shaped the first galaxies and set the stage for everything that followed. As pulsars age, their spins gradually slow, and their magnetic fields weaken. This aging process provides a unique opportunity to study the life cycles of neutron stars and the forces that influence their evolution. It also raises intriguing questions about the long-term behavior of pulsars. What happens to a pulsar after it has exhausted its rotational energy? Could these dead stars, sometimes called neutron star remnants, still play a role in the dynamics of the universe? Even as pulsars age and fade, their influence endures. The gravitational interactions of pulsars in binary systems, for example, have profound effects on their surroundings. These interactions can strip material from companion stars, trigger supernova explosions, or even lead to the formation of new celestial objects. In this way, pulsars are not only remnants of stellar death but also catalysts for cosmic renewal. The study of pulsars is also shedding light on the mysterious fabric of spacetime. Their signals, traveling through the gravitational wells of massive objects and the tenuous interstellar medium, are subtly distorted along the way. By analyzing these distortions, astronomers can map the invisible structures of the universe, from the tangled web of dark matter to the vast voids between galaxies. In recent years, scientists have begun to explore the potential of pulsars to probe the universe on even grander scales. Pulsar timing arrays, for instance, are being used to search for evidence of cosmic inflation, the rapid expansion of the universe in its earliest moments. If inflation occurred, it would have generated gravitational waves that rippled through spacetime to this day. Pulsars, as precise timers, could detect these ancient echoes, providing a direct window into the birth of the cosmos. And yet, even as pulsars illuminate the grandest questions of astrophysics, they also offer deeply personal insights. Their existence challenges us to think about time, change, and the cycles of creation and destruction that define the universe. A pulsar's pulse, so steady and enduring, reminds us that amidst the chaos of cosmic processes, there is an underlying order, a rhythm that connects all things. This connection extends to the most profound philosophical questions. Pulsars, in their ceaseless rotations, embody the tension between permanence and impermanence. They are both fleeting and eternal, their signals lasting far longer than the stars from which they were born. They remind us that while individual moments may pass, the patterns they create endure, weaving a tapestry that spans the cosmos. In the distant future, pulsars may become more than scientific curiosities or tools for exploration. They could serve as monuments to the ingenuity and curiosity of civilizations. Their signals, carrying encoded information about their origins and the universe around them, might one day be used to preserve the knowledge of a galaxy-spanning civilization, ensuring that its story endures even after its stars have faded. And what of the ultimate fate of pulsars? In a universe destined to expand and cool, they will be among the last active objects, their pulses slowing over billions of years until they fall silent. Even then, their remnants will persist, drifting through the darkened cosmos as silent witnesses to the universe's final chapters. Yet, even in this quiet end, there is beauty. The story of pulsars is a story of transformation, of resilience, and of the profound interconnectedness of all things. They teach us that the universe, for all its vastness and mystery, is not a cold, indifferent void but a place alive with rhythms, patterns, and stories that invite us to explore and to wonder. And so, as we continue to study these extraordinary objects, we are reminded of the infinite possibilities that lie before us. Pulsars, in their quiet persistence, inspire us to seek, to learn, and to marvel at the beauty of the cosmos. Their signals, traveling across the depths of space and time, carry a message that resonates across generations, that the universe is vast, that its mysteries are boundless, and that we are part of its grand and enduring story. The story of Pulsars weaves together the themes of time, space, and the enduring mysteries of the universe. Each pulse, traversing the infinite expanse of the cosmos, carries within it the tale of its origin, a tale of cataclysm and renewal. Yet, pulsars are more than relics of the stars that birthed them. They are cosmic lighthouses guiding us through the darkest corners of the universe and illuminating pathways toward understanding. One of the most compelling frontiers in pulsar research is their role as probes of the intergalactic medium. While much of pulsar study focuses on those within our galaxy, the detection of pulsars in other galaxies opens an entirely new perspective. Their signals, weakened but not silenced by the vast distances they travel, act as tracers of the material between galaxies, an environment that remains one of the least understood aspects of the universe. This intergalactic medium is the scaffolding of the cosmos, composed of gas, plasma, and perhaps even dark matter. Pulsars, with their predictable emissions, allow us to measure the density, composition, and temperature of this medium. By comparing pulsars in different regions of space, we can begin to map the unseen structures that connect galaxies, revealing the underlying framework of the universe. Pulsars also challenge us to confront one of the most profound and mysterious phenomena in nature, the arrow of time. Their steady pulses are unidirectional, moving forward without hesitation, a stark reminder of the one-way progression of time as we experience it. Yet, the existence of pulsars raises questions about whether time is truly linear or if it might loop or ripple in ways we do not yet understand. For instance, theories involving closed time-like curves suggest that under certain extreme conditions, such as near a rotating black hole, time might behave non-linearly. Could pulsars, especially those in binary systems with black holes, provide evidence for such exotic phenomena? By analyzing the timing and patterns of pulsars in these systems, scientists might uncover anomalies that point to a deeper, more complex nature of time itself. As we continue to study pulsars, we are also drawn to their connections with the origins of life. The elements forged in the supernovae that give birth to neutron stars are the same elements that form the building blocks of planets and living organisms. Carbon, oxygen, nitrogen, these were created in the heart of stars and distributed across the galaxy in the explosive events that also created pulsars. Some scientists speculate that pulsars may even play a direct role in the genesis of life. The high-energy particles they emit could contribute to the chemistry of prebiotic molecules in the interstellar medium, potentially influencing the development of complex organic compounds. This raises the tantalizing possibility that pulsars, far from being lifeless relics, might be part of the story of life's emergence on Earth and perhaps elsewhere in the cosmos. And what of the civilizations that might one day find themselves in proximity to pulsars? For them, these stars might serve not only as scientific tools but also as cultural symbols. Pulsars could be integrated into mythology, philosophy, and art, their unyielding rhythms representing endurance and cosmic order. They might even inspire new forms of communication or art, their signals transformed into music or visual representations that convey meaning across vast distances. The search for extraterrestrial intelligence, SETI, also intersects with pulsar research in intriguing ways. The regularity of pulsar signals makes them ideal candidates for natural beacons, but what if some pulsars exhibit irregularities that hint at artificial manipulation? Such anomalies could represent attempts by advanced civilizations to encode information or send messages using pulsars as intermediaries. While no such evidence has yet been found, the possibility keeps scientists and dreamers alike attuned to the subtle variations in pulsar emissions. Looking further into the future, the role of pulsars in humanity's cosmic journey becomes even more profound. As civilizations expand into the galaxy, pulsars will be essential navigational tools, their pulses serving as reliable markers in an otherwise featureless expanse. They will allow spacecraft to traverse interstellar distances with precision, offering a galactic positioning system that connects planets and colonies scattered across light years. Moreover, pulsars might become repositories of knowledge, their signals modulated to carry the history, science, and art of advanced civilizations. In this way, pulsars could serve as a kind of cosmic archive, ensuring that even if civilizations rise and fall, their contributions to the universe's story endure. But for all their utility and mystery, pulsars remain deeply poetic objects. They embody the paradoxes of the cosmos, born in chaos yet marked by order, fleeting in their individual lifespans yet enduring in their influence. They remind us that the universe is both violent and harmonious, both ephemeral and eternal. As we continue to study pulsars, we are reminded of the boundless curiosity that drives us to explore the unknown. They call us to listen, to observe, and to wonder. Their pulses, echoing across the ages, are a testament to the interconnectedness of all things, a reminder that even in the darkest reaches of space, there is light, and in the silence, there is rhythm. Pulsars are not just objects of science, they are symbols of discovery, endurance, and the infinite possibilities of the universe. Their story, like the cosmos itself, has no end, only new beginnings. And as we listen to their signals, we are reminded of the greatest truth of all, that we are part of this vast, mysterious, and beautiful universe, connected by the rhythms of stars that will pulse long after we are gone. The tale of pulsars unfolds endlessly, mirroring the vast, boundless cosmos from which they emerge. Their rhythmic signals, precise, enduring, and mysterious, act as a cosmic metronome, measuring time across unimaginable distances and eons. Yet, pulsars are not static, their existence is deeply dynamic, reflecting the ever-evolving universe in which they reside. One area where pulsars continue to captivate scientists is their role in understanding the cosmic web. This immense structure of filaments, composed of galaxies, dark matter, and intergalactic gas, spans the universe, connecting everything like a vast neural network. Pulsars, particularly those outside the Milky Way, offer a unique means of probing these filaments. Their signals, traveling through intergalactic space, carry subtle distortions caused by the matter they encounter, providing clues about the density, temperature, and composition of the universe's connective tissue. This ability to act as intergalactic messengers places pulsars at the forefront of cosmological research. By detecting and studying pulsars in other galaxies, a feat made possible by next-generation telescopes like the Square Kilometre Array, scientists can extend their reach across the observable universe, using pulsars to trace the evolution of cosmic structures from the Big Bang to the present. Pulsars also serve as invaluable tools in unraveling the mysteries of dark matter, the invisible substance that constitutes about 27% of the universe's total mass energy content. One intriguing theory suggests that interactions between dark matter and pulsars could produce faint, detectable changes in their emissions or rotational behavior. By monitoring pulsars with ever-increasing precision, we may one day uncover the fingerprints of dark matter, shedding light on one of the greatest enigmas in modern physics. But pulsars are not only windows into the universe's largest scales. They also offer insights into the smallest, most fundamental particles. The extreme conditions within neutron stars compress matter to densities far exceeding those found in atomic nuclei. This makes pulsars natural laboratories for studying the behavior of matter under conditions impossible to replicate on Earth. In particular, the cores of neutron stars may harbor exotic forms of matter, such as quark-gluon plasma or even strange matter, states that existed only fleetingly during the universe's earliest moments. Understanding these states could revolutionize our understanding of the fundamental forces that govern the universe, linking astrophysics with particle physics in profound and unexpected ways. Pulsars also challenge us to think about the nature of energy and magnetism. Magnetars, a rare and extreme form of pulsar, possess magnetic fields so intense that they can distort the shapes of atoms and generate bursts of energy that outshine entire galaxies. These titanic eruptions, known as soft gamma repeater flares, represent some of the most powerful events in the cosmos. By studying magnetars, scientists hope to better understand the mechanisms that create and sustain such immense magnetic fields, offering insights into magnetic phenomena across the universe. The role of pulsars as cosmic tools extends beyond science. They are also practical allies in humanity's journey toward the stars. As interstellar exploration becomes a tangible goal, pulsars will play a pivotal role in navigation. Their regular signals, unaffected by the passage of time or the chaos of stellar environments, provide a galactic framework that can guide spacecraft with unparalleled precision. Imagine a future where pulsars form the backbone of a galactic positioning system, GPS, enabling humanity to traverse the galaxy as easily as we navigate our own planet. This concept, once relegated to the realm of science fiction, is increasingly becoming a reality, with experiments already demonstrating the feasibility of using pulsars for autonomous spacecraft navigation. Even more profound is the potential for pulsars to act as cosmic archives, preserving the knowledge and history of advanced civilizations. Their signals, modulated to encode information, could carry messages across the galaxy, enduring long after their senders are gone. In this way, pulsars could become the librarians of the universe, safeguarding the stories of stars, planets, and civilizations for eternity. As we imagine these possibilities, pulsars also invite us to reflect on the nature of time and existence. Their unyielding rhythms remind us that time is both a relentless force and a unifying thread. A pulsar's pulse, repeating over millions or billions of years, offers a sense of permanence in an ever-changing universe. Yet it also reminds us of the fleeting nature of individual moments, encouraging us to appreciate the beauty and wonder of the present. Pulsars, in their paradoxical combination of simplicity and complexity, serve as metaphors for the universe itself. They are born in the violent deaths of stars, yet they emerge as beacons of order and stability. They are relics of the past, yet they illuminate the future. They are distant and untouchable, yet their signals connect us to them, and to the cosmos at large. As we listen to their pulses, we are reminded of our own place in the universe. The atoms in our bodies were forged in the same stellar furnaces that gave birth to pulsars. The light we see from these distant objects has traveled across the same space that surrounds us. In studying pulsars, we are not only exploring the universe, we are discovering ourselves. And so, the story of pulsars continues. It is a story of stars and galaxies, of forces and particles, of chaos and order. It is a story of exploration, curiosity, and wonder. Most importantly, it is a story that invites us to look beyond ourselves, to embrace the infinite, and to marvel at the mysteries of existence. The pulses of these distant stars echo across the cosmos, carrying with them the whispers of creation and the promise of discovery. They remind us that the universe is alive with rhythms, patterns, and meaning, and that we are part of this grand and beautiful symphony. Pulsars are more than the remnants of stellar death, they are beacons of resilience, precision, and cosmic wonder. Born from the cataclysmic collapse of massive stars, they transform destruction into harmony, chaos into rhythm, and silence into a pulse that echoes across time and space. These enigmatic objects serve as natural timekeepers, cosmic laboratories, and galactic signposts. They guide us in our search for answers to the universe's most profound questions, about the nature of gravity, the behavior of matter under extreme conditions, and the invisible forces that shape the cosmos. Pulsars illuminate the history of galaxies, the dynamics of spacetime, and the processes that forge the elements of life itself. Yet, pulsars are more than tools of science. They are symbols of endurance and interconnectedness, linking us to the stars and to the grand cycles of creation and transformation that define the universe. Their ceaseless rhythms remind us that even in the darkest corners of space, there is light, even in silence, there is a pulse. As humanity stands on the threshold of interstellar exploration, pulsars will guide us, their signals pointing the way through the vastness of the cosmos. They will serve as navigators, storytellers, and archivists, preserving the history of the universe for generations yet to come. In their persistence, pulsars reflect our own quest for understanding, a quest driven by curiosity, wonder, and the desire to connect with the infinite. Their pulses, traveling across the eons, invite us to listen, to learn, and to marvel at the beauty of a cosmos that is both mysterious and knowable. And so, the story of pulsars continues, as boundless and enduring as the universe itself. Their signals remind us of the infinite possibilities that lie ahead and of our place within the grand, unfolding narrative of existence. Pulsars teach us that in the rhythm of the stars, we find the heartbeat of the cosmos, and in that rhythm, we discover ourselves.